is the lecture for 4.5 and 4.6. I'm combining them because the topics are so involved with each other that it doesn't seem like the way to do it to separate them. So 4.6 and 4.5, I like to do 4.6 first because that's the algebra of log rules, okay? Then 4.5 is the derivative of the log rule. So it just makes more sense to me to talk about the algebra first, just like we did with the exponents in 4.1, then 4.2, 4.3 for the derivative rule for the exponentials. So for 4.6, algebra rules, for logarithms, we have 3 rules. First one is very similar to the first exponent rule. If you had same base, right, you added the exponents if you multiplied, right? So if it's, remember, exponents and logs are backwards, they're inverses, so the opposite of true. So if we have the natural log of x plus the natural log of y, those are added together, so then the answer is multiplication. So it's the natural log of x times y. The kind of bases are the same, but it's both ln, so then we multiply their insides, the x and y's together. The next rule is the opposite of this. It is similar to the division rule for exponents. So the natural log of x minus the natural log of y is equal to the natural log of x over y. So just like plus goes to multiplication, minus goes with division. All right? Then we have one last rule. If we have a coefficient on a natural log of x, we can rewrite this as the natural log of x to a power of a, of that coefficient, okay? So that a is on the x, the natural log of the quantity x to the a. All right, so those are our 3 rules. If anyone has any questions on those, please ask now to the substitute. All right, so rules, using these rules in problems, we can just generally simplify just like we did in 4.1 with the exponentials. So say we have 1/2 of the natural log of 36. That is that third rule that we learned just now. So the coefficient can be moved up to be a power. So we have the natural log of 36 to the 1/2 power. Well, we can do more with this. We know the 1/2 is really just a square root, written a different way. So then this is really just ln square root of 36. Again, one more step of simplification. Now, square root of 36 is 6. So this is really the natural log of 6. We would stop here because any further, this would be putting it in our calculator and getting a decimal that we would need to round. Unless they tell us to round to a specific place, we can assume that they will almost always want an exact answer, okay? So then, another example is if we have e to the natural log of z to the 4th plus 8 natural log of x. We want to simplify this. Now sometimes it's a little difficult to see on these if we've got simplified enough, okay? Pretty much we can assume that we need to use log rules somewhere in the problem since it's in this section, okay? It's usually kind of a good hint for us. So we recognize here that while we have an e with multiple ln's, so we're probably going to want to cancel at some point, but we can't yet because we don't just have e with a single ln yet. So first we need to look and see, well, maybe, okay, there's a plus with 2 ln's. Can we add them together yet? No, because of this 8, this coefficient. So we need to do something with the coefficient first. Well, just like the last one we did, let's move the coefficient up to be a power. So first step, multiplying, we have e to the natural log of z to the fourth plus the natural log of x to the eighth. Now, well, addition with logs, we know we combine and multiply their insides. So this is e to the natural log of z to the fourth times x to the eighth. Doesn't matter what order, could be x to the eighth times e to the fourth. Now we have an e with a single ln. These can cancel because they're inverses, right? Just like we learned in 4.4. So then the inside the natural log drops down. So z to the fourth times x to the eighth, that's our answer. That's as simple as it gets. And I think we can all recognize that this is as simple as it gets. We wouldn't be able to do more with this. Okay? Next example is they tell us in one problem to use the fact that the natural log of 3 is approximately, that's what the curly equal sign means, right? They tell us 1.1. They've essentially calculated it and then truncated it to a specific place. And the natural log of 5 is approximately 1.61. Now they want us to use those facts in problems such as the natural log of 1 over 15. So we need to somehow get this to involve the natural log of 3 and or the natural log of 5, okay? There's one other one that we need to remember that we talked about last Tuesday. That would be if, right, if we have the kind of inverse point for all the graphs that we talk about with exponentials and logs, that the natural log of 1 is equal to 0. We do need to remember that piece. So now we look at this problem specifically and we see, well, we have a division inside of the ln. We can go backwards, right? Break that apart into multiple ln's. So division, we know, goes to subtraction. This is the natural log of 1 minus the natural log of 15. Natural log of 1 we know is 0. This just essentially cancels out then. Now, 15 is 3 times 5. Well, that's getting us to our 3's and 5's, right? Multiplication inside we know is addition on the outside. So we need to think about this negative outside though. That is a coefficient essentially. It's on both pieces. Or just put it in parentheses on the outside. So negative ln of 3 plus ln of 5, because 3 and 5 make 15. So then we can just use the approximations. So we have negative ln of 3 is 1.1 plus ln of 5 is 1.61. Add together, so we get negative 1.1 and 1.61 is 2.71. That would be our answer to this problem. Any questions? Okay, next part of this one is if we're given the natural log of 5 over 9. Again, this is a division on the inside. We can break this up as natural log of 5 minus the natural log of 9. Before we start plugging in for the natural log of 5, let's make it be all either 5's or 3's. We recognize that 9 is 3 squared though. So this is really the natural log of 5 minus natural log of 3 squared. Well, it's still not natural log of 3 though. This exponent can be brought down out front, right, as a coefficient. So we have the natural log of 5 minus 2 natural logs of 3. Okay? Now that it's all natural log of 5 and natural log of 3, now I would plug in. So we have 1.61 minus 2 times 1.1. So this is 1.61 minus 2.2. So subtracting, that would give us negative 1.41, I believe. That would be our final answer. Okay? Last one is if we're given the natural log of 1 over the 5th root of 5. Again, starting out with division. So this is the natural log of 1 minus the natural log of the 5th root of 5. Natural log of 1 is 0, so it goes away. We can rewrite this as a power. So this is really minus natural log of 5 to the 1/5. Square roots are 1/2, cube roots are 1/3, right? Yeah. Power of the exponent just is the denominator of the, the power of the root is the denominator of the exponent. So then again, it's an exponent of the inside, can be rewritten as a coefficient. So minus 1/5 ln of 5. Now, because it's again just ln of 5, we can go ahead and plug in. So we have negative 1/5 times 1.61. Okay? We can just plug that in our calculator. I'm not going to do it in my head and make the mistake. Okay? So next is if we were given something like the natural log of x minus the natural log of x squared plus the natural log of 3 is equal to 0. So in this type of problem, we are again solving for x. So we can do it a couple different ways. The easiest way would probably be to say that, well, okay, this is a minus. Minus outside means division of the insides, right? So that means the natural log of x over x squared. We always need to do these from left to right, like we're reading the problem, okay? Still plus the natural log of 3 equals 0. So then we can simplify this. X over x squared is really just the natural log of 1 over x. Still plus the natural log of 3 equals 0. Plus, on the outside of ln's, means multiplication of their insides. So we have the natural log, 3 times 1 over x, that 3 just goes in the numerator. So 3 over x is equal to 0 now. So, we want to solve for x, meaning we want to cancel out the ln. We use its inverse. So we raise both sides to the e, meaning the e and the ln cancel. So we have 3 over x left on this side equals e to the 0. Anything to the 0 is 1. Finish solving for x by multiplying it over. So x is equal to 3. Now we should always make sure on these that our answer makes sense and works in our original problem. Most likely, because we only got one option, this will give us a valid answer. So, let's make sure though. We can plug in positive 3 into x, right? It doesn't give us a negative inside. That's generally what we need to check for. So that one's good. Well, 3 squared is still positive, so that one's okay as well. We already had ln of 3, that's a positive inside. So, x equals 3 is a valid number to plug in. If we wanted to check that the value was correct, not just the sign, well then we could use our calculator, okay? Alright, then another problem very similar to this is if we have the natural log of x to the 4th minus 2 natural log of x equals 3. So again, we're solving for x. So, well, we have multiple x's. We probably want to put them together somehow. This too, this coefficient needs to be rewritten as the exponent first before we can combine them. So we have the natural log of x to the fourth minus the natural log of x squared still equals 3. Now we can use the minus to divide the insides. So the natural log of x to the fourth over x squared equals 3. X to the fourth over x squared, well, two of them cancel to leave us with 2 in the numerator. So then we have natural log of x squared equals 3. Just like last time, we need to cancel out the ln by taking e to both sides. So the e and the ln cancel. We have x squared is equal to e cubed. So now, we're still not finished solving for x, right? So we have to take the square root of both sides, okay? However, when we take the square root, we know we get x equals plus or minus square root of e cubed, okay? Again, we need to check. If we plug the positive version in, well, a positive answer usually is good, but positive answer to the fourth power is a positive number. Positive plugged in just x is positive, so we're good. What about the negative? Well, negative to a fourth power to any even power is positive. Negative, well, we can't plug in a negative to ln, so the negative square root of e cubed is not valid. We only have one answer here, just the positive square root of e cubed, okay? Always check on those, because obviously sometimes not all of your answers work. Alright, so those are the examples for 4.6 rules that I wanted to do for the algebra. 4.5, going backwards, is the derivative of log. So that rule is the d dx, taking the derivative of a coefficient of ln of a some quantity of x. We call it g of x, just like we did with the exponential functions. So now, what we're doing is we rewrite the coefficient times a fraction, okay? In this fraction, the denominator is what was inside the ln. So the g of x goes on the bottom. Now, what goes on top? G prime. We take the derivative of the inside and put it in the numerator of the fraction. So our answer will always be a fraction, okay? The coefficient times g prime over g. So let's do an example. If we have y is equal to 5 natural log of 9x. So y prime is equal to, we rewrite the coefficient, so the 5 drops down, times the derivative of the inside, so the inside is 9x, derivative of 9x is 9, over the entire inside, 9x. We can simplify this, however. So we have 9 over 9. Those cancel. This 5 is over 1, so when we multiply them, that 5 is in the numerator. So this final answer is 5 over x. Okay? So we, again, like we said, will always get a fraction, and generally the ln is not in our answer, okay? So we do not include the ln, just its inside, what's inside of the function of natural log. So then, what if we had y equals the natural log of x plus 5 plus the natural log of 9, taking the derivative again. So this first ln, do it term by term, has a coefficient of 1. We don't need to write it. So the derivative of the inside, x plus 5. Derivative of x is 1. Derivative of plus 5 is 0. So our derivative is 1 over the entire inside of x plus 5. Now on the second term, we need to be very careful. Remember, when we're taking derivatives, we need to look for a variable. ln of 9, there's no variable there. This is a number. It's not a very nice looking number, okay, because if we plugged it into our calculator to actually get its numerical value, we would get some ugly decimal, right? That's why it's written as ln of 9. However, though, like we said, it's just a number. So the derivative of a constant is 0, meaning this 1 over x plus 5 is our answer. That is our full derivative. So then, if we want to take the derivative of the natural log of x to the 13th power, all the natural log of x is to the 13th, not just the x, plus the natural log of x to the 13th. This is just x to the 13th, so they're opposites of each other, essentially. Okay? Again, we're taking the derivative. So, with this first term, we need to recognize that this is a function inside of a power. Okay? That means this is a general power rule, or a chain rule. Okay? Specifically, though, a general power rule. So we always start there on the outside by bringing the power down. So 13, keep the inside the same, take away 1, so 12. Then the derivative of the inside. The inside here is ln of x. So let's think about that one separately for a second. ln of x. The derivative would be derivative of the inside. X is 1 over the inside. So the derivative of ln of x is 1 over x. So we're multiplying by 1 over x here. Then plus the derivative of ln of x to the 13th. So again, we start out by taking the derivative of the inside. The derivative of x to the 13th is power rule, 13x to the 12th, over the entire inside of x to the 13th. So now we can do a little simplification. 13 and 1 over x, we don't really need to simplify this part of the term, but it can help it look a little better. Is just 13 over x times natural log of x to the 12th. Plus now, on this term we have 12x's over 13x's, meaning we can cancel out 12 of them and be left with one of them in the denominator. So we have 13 over x. This is our final answer. That's our full derivative. So then, what if we're given y is equal to 3 ln of 14 over x? So sometimes, before we start taking the derivative, we want to do a little simplification first. Always look to see if there's any simplification to do with both exponentials and logarithms, okay? Because generally, there's some simplification that we can do that actually makes it much easier, okay? There's some complicated steps to do in this one specifically if we do not simplify it first. So, the simplification that we need to do is we need to recognize division on the inside means subtraction on the outside. So, just algebra, no calculus yet, we rewrite the 3 on both of them. So, ln of the top minus ln of the bottom, okay? Then go ahead and distribute the 3 through. So y is equal to 3 ln of 14 minus 3 ln of x. Now we can take the derivative. Again, this is just a number. There's no variable here. The derivative of a number is 0, so it goes away. Minus 3 is the coefficient, so it gets rewritten, times derivative of the inside, which is 1, over the inside, which is x. So this is really just negative 3 over x, okay? That's our final answer again. That's our full derivative. Okay, so then if we have y equals the square root of ln of e to the 2x plus 4. We want to take the derivative again. Before we can do that, however, we need to simplify it, rewrite it. So y, just algebra, is the natural log of e to the 2x plus 4 to the positive 1/2, just rewriting the square root. Now it's rewritten as a quotient, general power rule. We can take the derivative. So y prime is equal to, bring the power down, so 1/2, keep the inside the same, take away 1, so negative 1/2, times the derivative of the inside. The inside is a natural log, so then we look at its inside. The derivative of e to the 2x, we look at its exponent. Derivative of 2x is 2. So 2e to the 2x plus the derivative of 4 is 0. So plus 0 if we wanted, right? Over the full inside of the natural log. E to the 2x plus 4. Any questions at that stage? Okay. So then we could do one little simplification in that we have 1/2 here and a 2 in the numerator here. Those just cancel each other out, okay? So that our final answer for our derivative is the natural log of e to the 2x plus 4 to the negative 1/2 times e to the 2x over e to the 2x plus 4. These e to the 2x's do not cancel because of this plus 4, right? We would need an e to the 2x in every term before we could cancel it out. But that is our final answer for our derivative. Okay, so then if we are given a cost function, c of x is equal to 49 ln of x over 42 minus 5x, we're told to find the marginal cost when x is equal to 7. So we know marginal means derivative, so we need to find the derivative of this function. Well, there's an x in the numerator and an x in the denominator. That means this is a quotient rule. So f is equal to the numerator, 49 ln of x. G is equal to the denominator, 42 minus 5x. So then f prime is equal to, rewrite the coefficient, times the derivative of the inside over the inside. G prime is equal to, 42 is 0, minus 5x is minus 5. Quotient rule formula, so c prime of x is equal to f prime times g. So 49 times 1 over x is really just 49 over x. That's the best way of writing it. So 49 over x times the quantity, so parentheses, of 42 minus 5x. Quotient rule, so must be a minus sign. G prime times f. But g prime is a negative, so we're doing minus a minus. So really plus 5 times 49 ln of x. All divided by g squared. So 42 minus 5x squared. Now, we were told, find the marginal cost when x is equal to 7. So that means now that we have the marginal cost formula, the C prime, we need to plug in 7 for x. So C prime of 7 is equal to 49 over 7 times 42 minus 5 times 7. I totally did not leave myself enough room, so then plus 5, 49 ln of 7 divided by 42 minus 5 times 7 squared. Okay, so 49 divided by 7 is 7. 5 times 7 is 35. 42 minus 35 is 7. Plus, now this one we're just going to leave alone. Leave it as 5 times 49 ln of 7. You'll see why in just a minute. Over, we already calculated this. We know that it was 7. So then we have 7 squared. 7 squared is 49. Notice here, we have 49 in every term because 7 times 7 is 49. So 49 here, 49 here, and 49 here. Because it's in every term, we can cancel. Cancel the 49, the 49, and the 49. So that means we canceled it out, but we still need the placeholder for the term of 1 plus 5 times ln of 7. This is our answer, I think. Yes, because they want you to rewrite it and submit the answer in exact form. So this would be the formatting. Okay? So then, if we want to take the derivative of the natural log of the quantity of x plus 2 times 5x minus 1 times 5 minus x, we need to do a